Juan is there, and we can start with questions to Juan. Anybody wants to ask a question to Juan concerning his talk? Andrei Panochev, please.
Hi, thank you for a very nice talk, Juan. I have a question for you. Can you hear me?
Yeah, I can hear you.
My question is related to some of the things that you mentioned about the NS5 branes at final temperature. So the near horizon description of that system, as you mentioned in your talk, also involves the same kind of coset. But I think if I remember well, if you study the thermodynamics of that system, the temperature at tree level is fixed, and to change it, you have to do a one-loop computation, which Kutasev and Haken did, and you find that the system has negative specific heat, just like the system that you were discussing, but the temperature is always above the Hagedorn temperature. So you're always describing the phase, some weird phase. And then there are all sorts of, like if you study the system, if you study correlators in that system, you observe that there are all sorts of instabilities and so on. So I apologize, but I would like to ask two questions related to it. The first question is, do I understand it correctly that in this setup that you're describing, situation is much better? So you can change the temperature at tree level, can go above Hagedorn temperature, below Hagedorn temperature, and everything, because you can do calculations, everything is well defined at tree level. And the second question is, so asymptotically, this situation is the same as the NS5 brane situation. And there you could try to come up with some kind of holographic interpretation of the theory on NS5 branes by studying correlators in linear Newton theory, basically. So if you, and there, that's where you see all these instabilities. So can you do something like this in your case?
Well, let's first talk about the first question. So the way the cigar theory is embedded into the full string theory is different in the two cases, in the NS5 brane case that you mentioned, and in the case we are considering here. In the case we are considering here, maybe I should have. So the cigar theory has some parameter we call K, and the temperature is fixed in terms of that K. In the 5 brane theory, K is quantized and is the flux related to some flux through some other dimensions. And so that flux is fixed, and for that reason, you cannot change the temperature at tree level. In our situation here, K is related to the size of some extra sphere, and that size can be changed. So you can change K and you can change the temperature. So that feature is different. So the connection to the physical temperature and what the parameters are is different. It is still true that for a given K, there is only one temperature. But in our situation, when you change that temperature, K also changes. So physically, you can change the temperature. Okay, so that's the comment related to the first question. Now, for the second question, I guess there is no clear holographic dual of the NS5 brane. So, and yeah, here I don't know. We haven't thought about holographic duals, but I would imagine it would be as unclear as in the case of the 5 brane.
Yeah, I think people try to make sense out of.
Yeah, what people have done is to take this background and study correlators in this background just to learn at least what properties possible holographic dual would have, but there is no independent definition of a holographic dual.
Thank you.
Yeah, sure.
Other questions? maybe I can ask you one question. I can ask you one question, Juan. I have vague reminiscences of a very old paper of Attic and Witten in the 80s.
Yeah.
That was somehow adding some understanding to the Hagedorn transition in string theory. Does it have any bearing on your current understanding of the problem? Is it related in some way, or?
Yeah, there is some relation to, not directly to what I discussed, but to the solution of Horowitz and Polchinski I referred to. So let me try to say what Attic and Witten said. So they wrote this action that we discussed, and they consider configurations where the winding condensate was constant, okay? And they said, well, you have two fields. One is the winding condensate field, and the other one are all the massless fields, let's say graviton, dilaton, etc. And the idea was that if you integrate out these massless fields, you would get an effective quartic term for the winding mode with a negative coefficient. So the total potential would be a positive. Let's say we are at a temperature higher than the Hagedorn. Temperature lower
so
than
you get an expectation value somehow.
What?
Would get an expectation value at that point.
Well, the idea was that
no, not even, because it's unstable.
Sorry.
Okay. Go ahead.
Yeah, the idea is that there is, to leading order, there is a quadratic potential, right, for the chi field, and the question is where there is a quartic potential, right? Now you can calculate that. You can calculate this in string theory, and you find that there is actually a positive quartic potential at string. Just naively, just computing the scattering of four of these winding modes. However, it turns out that there is a bigger effect which comes from integrating out the massless modes, which gives rise to a negative potential, which is more dominant. Mm-hmm. So the full effective potential is it's a negative quartic potential, and then we have this mass square term which changes sign when we go through the Hagedorn transition. So what they said is that because we have this negative potential, the transition.
You think was first order.
First order transition, right? Okay, so this Horowitz Polchinski solution can be viewed as giving you a kind of tunneling solution that tunnels from the flat space without winding to the region where you condense a bubble of this other vacuum.
Okay.
So that's sort of an alternative interpretation, but so it is connected to.
So they didn't have a sixth order term, but they found this negative quartic term and then assumed that the sixth order positive term would exist somehow, and then they argued in terms of a first order transition, right?
Yes.
Thank you very much.
Yeah.
Any more questions for Juan?
Let me just say again why this term is negative. So give a more intuitive explanation. So it's related to the fact that the gravitational interaction reduces the energy, right? So you have some string, let's say some gas of strings, and when you include gravity, you kind of reduce the energy. There is a negative binding energy.
But how do you talked about integrating out the massless modes, but what do you mean by that precisely? I mean, I understand integrating out massive modes, but massless modes in what sense? I mean, they appear like.
Well, yeah. So this is just another way of saying that we just include the effective gravitational potential interaction, right?
Okay.
So it's like essentially the Newtonian potential.
Okay, so you basically.
Yeah, it's basically the same as what I was saying about including the gravitational interaction, and that you would get a negative contribution from this gravitational interaction.
Okay.
It is not more than that. It's just the same as saying that.
Thank you.
Yeah.
So, are there more questions for Juan? Okay, if there are no more questions for Juan, we can move to Axel. Thank you, Juan, for the talk and the discussion. And Axel, who wants to ask a question to Axel? I have a couple, but I will wait for other people to ask. Zhenya and Misha. I don't know the order. I just saw two hands. Let me start from Zhenya first, and then.
Many thanks. Actually, can you hear me?
Yes. Yes.
So the question is about wildness of E11. So your action and equations, I suppose, are highly nonlinear, and due to this fact and wild infinite dimensionality of E11, can you accumulate some infinities? Do you need to require some components of your fields to decay somehow when you go high up in this level? So can be problems of this type, or everything is well defined?
So indeed, this is something that you have to worry about, and there's a particular way. I mean, so I was writing this thing in terms of this generalized metric, which was this infinite by infinite matrix, and you have to choose a particular parameterization of this infinite by infinite matrix to make sense of the terms that you get in the action. But there's a parameterization that you can do, and in some sense, it's just a local choice of coordinates for the fields. And then you do not accumulate any infinities that you have to regulate away. I mean, first of all, there's no notion of sort of infinitely far. So the question is not so much about decay properties of the fields, but the question is more like when you take variations to compute Euler-Lagrange equations, whether they are well-defined or infinite sums that sort of need to be regularized. And then by choosing the right parameterization, it doesn't happen. But indeed, it's something to worry about, and but we think we have this under control. So in that sense,
in some sense, one can say that.
So in that sense, I mean, it's an infinite dimensional algebra, and it's quite wild. But I mean, typically the things that we write down, they are written in this highest weight module. So that means that if you act in the right direction in this module, you will only see a finite number of states. So that's one of the things that makes things finite, together with the section constraint.
Okay, so just let me repeat. So you need to choose specific coordinates in this space to ensure that everything is finite, right? So it's not just
it's not. So it's not coordinates. It's not coordinates in this space of which I call ZM or something like this, of this infinitely extended space, which is sort of just an artifact. But what I'm talking about is a specific coordinate choice on field space.
Yes.
So
okay.
You have to parameterize the fields in the right way to get finite expressions for these nonlinear interactions in the Lagrangian.
Thank you.
So I see a few hands up, but nobody's daring.
Actually, I have a question to you. Is it true that this section constraint preserves all symmetries of the original theory, or it breaks it somehow?
So the constraint is written in a way that preserves all the global symmetries.
Yes.
But when you make a solution of the constraint, so you pick a solution, then you break the symmetries. It's like spontaneously broken by a solution, but the equation itself is has all the symmetries.
And how is this symmetry realized on 11-dimensional supergravity? I mean, all symmetries, original symmetries, somehow realized, or some nevertheless become trivial or something like this.
So yeah, so the thing is that I mean, the equation has this infinite dimensional symmetry. If you pick a solution, you break the infinite dimensional symmetry, and what you break it down to is exactly the symmetries of 11-dimensional supergravity. So we see no traces of new symmetries of 11-dimensional supergravity from this.
So they are somehow compensated, yes? Some kind of compensators in the multiplet or something like that.
So I think it's just the fact that, I mean, the solution that there's no like nonlinear realization or Goldstone field or anything like this. I mean, the section constraint is a bit peculiar, let's say. I mean, it's something that is weird geometrically. And when you pick a solution, it's like picking a certain subspace of this infinite dimensional space, and only in this subspace is 11-dimensional supergravity defined. When you make a rotation, so you change the solution of the section constraint with a global symmetry, you actually also move out of 11-dimensional supergravity. So it's not a symmetry of 11-dimensional supergravity, but it's a map from 11-dimensional supergravity to a different theory. So there are no symmetries within 11-dimensional supergravity from that.
My last question is the following. You mentioned, I suppose in answer to Igor Banda's question, that this pseudo-Lagrangian is needed for you only for deriving equation of motion. But when you derive equation of motion from the standard principle, you always assume that full derivative is vanishing on the boundary. But in this case, if you have no any integration, how you derive the equation of motion? I mean, you derive up to some.
We derive up to total derivatives. So we do integration by parts and we throw them away. Yes.
Yeah. Yes. So you just move it away. I mean,
yeah.
throw away this thing.
Yeah.
Can you please educate me and maybe some others who are not experts? So I heard about E8.
Sorry, do you hear me? There were two people that asked two questions. They wanted to ask questions. One moment. There was Misha and Karapet.
Oh, okay.
But then I'll come to you.
Okay.
As soon as possible. Misha?
Okay, thank you. I have actually the following kind of trivial question that followed from the answers to the previous ones. So once you say that the resulting theory is just 11-dimensional supergravity, number one, and then you say that all other symmetries are broken down to the symmetries that are known to be there in 11-dimensional supergravity. My question essentially is why it is useful to have this formulation. I'm sorry for asking this.
No, that's an excellent question. So the reason is that you have to solve the section constraint, and when you take a particular solution of the section constraint, you just get 11-dimensional supergravity. Yeah. But you can also choose different solutions of the same constraint, and then you get different theories. So one attraction of these exceptional field theories, and as you say, it's not really only about E11, is that they combine all the different supergravity models in one single framework. So it's sort of a unifying framework, and people have used this unifying framework to construct things like generalized Church-Schwarz reductions, classifying certain brain solutions, and so on. I mean, you can do something with the framework. It's not just some.
But the symmetry is really huge, isn't it? Yep. So it's somehow I would expect this would imply that the the variety of all different supergravity theories is as huge as roughly as that symmetry is, or the number of orbits somehow, or how huge it is. Can you just tell us what should we expect?
I mean, I don't know how to quantify infinity in that context.
Yeah.
So it's certainly infinite. Yeah.
My understanding of the story is that up to, say, 3 dimensions, you have E8. 2 dimensions, you have E9. 1 dimension, you have E10, which is already infinite dimensional. And then you go formally to 0 dimensions. So space-time has disappeared, and then you make it re-enter via these formal coordinates Z, because they have nothing to do with space-time a priori, right?
Well, they are the ones that become the space-time coordinates. So normally,
eventually, but I mean, the space-time coordinates have disappeared to manifest E11, right?
No.
It would be manifested only in the cosmological solutions, which have only one, say, dimension where non-trivial dynamics takes place. To get the 11, you have to destroy space-time.
No, I would disagree with that, actually. So the way that it works, and I mean, this is not only about E11, but about any exceptional.
Sorry, Andrea.
About any exceptional field theory. I mean, you do a split. I mean, you start with 11, you split it somewhere in the middle, let's say 4 plus 7.
Yes.
And then you would say, okay, if I go down to 4, I have E7, but you can also write down the 11-dimensional theory by extending the 7-dimensional space even further. And this is what exceptional field theory does. And then you haven't really lost these 7, what are normally called internal directions in the process. So you haven't destroyed this space-time. You've replaced it by something even more elaborate. And this is what we're doing for 11. So we are completely removing what is normally called the external space, and we're replacing the 11 internal directions by something very elaborate, but it's
Okay.
we're not really destroying the
That-
space-time.
Yeah,
It's
okay.
just a way of
No, the
rearranging things.
space-time is removed, but the internal part is made more elaborate. Okay.
Yeah, yeah.
Okay.
But-
Can I get,
Please go on.
Yes. Hi.
Hi.
So my question is some variation of earlier questions, but maybe you could elaborate a bit more on this. So so basically, once you get to the point when everything is formulated in terms of internal coordinates, then you can pick a certain solution to your section constraints, and in this situation, somehow you can effectively, you have a possibility to find much more theories than what you started with, right?
In principle, yeah, yeah. So you would have to classify all these possible solutions and all these theories. Yeah.
Is there any classification of the?
No, so this goes back to the question of like, how big is the space of solutions? And as I said directly after the talk, I think the maximal dimension that you can get for sort of a space-time is 11 dimensions. And then in some sense, all the other options that you have are the usual maximal supergravity theories, but you can get gauged, or you can get sort of Romans mass deformed, things like that. But there's no example that I'm aware of that has been constructed in this way that wasn't known by other ways. But here, because it's so infinite dimensional, it's certainly something that should be explored more. I mean, we haven't really played with that.
Is there a chance, for example, that the reason why we don't find anything new is that we look for what we know somehow? For example,
Yeah.
one could consider a possibility with different signatures.
Yeah, so
anything like that?
So yeah, so this is something that I didn't want to get into. So at some point I said you have to put something like the generalization of the Minkowski metric somewhere. And in fact, this generalization of the Minkowski metric, there are different 11-dimensional versions of that space. Some of them have signature 1,10, others have signature 2,9, yet others have 5,6. And these, but in fact, this is also something that was known differently, because these are the spin groups that have 32 real spinor representations. These are called M star and M prime theories by Chris Hull.
actually,
these are also part of that.
There's even a peculiar case in 12 dimensions where you can put Majorana-Weyl spinors.
That's correct. Yeah, yeah. But we haven't found like F theory or this 12-dimensional.
I think Andreas Milke has been waiting for a long time.
Yes.
So again, just I want to understand, maybe learn something. So I heard kind of rumor, let's say, I never, cannot say whether it's true or not, that 11-dimensional supergravity has a hidden E8 symmetry, and that it's not a symmetry of the Lagrangian, but it's the symmetry of equations of motion.
Mm-hmm.
The first question, is my recollection correct? And then the second question, is there some, similarity between this E8 symmetry and E11 symmetry, which you study?
So say again, so the rumor that you heard is that which theory has E11, E8?
11-dimensional supergravity.
Okay, so this is...
They were works of Kramer and Julia, right?
Yes.
And they discovered, as far as I understand, E8 symmetry at the level of equations of motion, but not the symmetry of the Lagrangian.
But this is not in 11 dimensions, this is in 3 dimensions. This is after reduction.
After reduction.
Yes.
So it's, it's n equals 8 supergravity in 3 dimensions, right?
N equals 16, I think, but yeah. I mean the maximum.
N equals 16. And n equals, and 11-dimensional supergravity doesn't have any symmetry.
It does,
just direct symmetry of Lagrangian or of equations of motion.
Internal symmetry.
Yeah, so this is, in some sense, the underlying motivation for many of these works. Is there a way to make it E8 or E7 or E11, any of these act directly in 11 dimensions? And so far, all attempts have failed. I mean, that's also what I was trying to stress, that, I mean, we have E11 somewhere, but once we specialize to 11 dimensions, the symmetry goes away. And the same is true for E8.
Okay, thank you. And so what you are doing, this E11, well, is not the same as this 8. It has another status. It's something different. Well, this E8, as you said, in a dimensionally reduced already theory in 3 dimensions. Maybe this theory also has some larger symmetries. So your E11 has nothing to do with this 8.
No, you can recover this E8 also from what we were doing, and we do this in the paper. So E11 has a subgroup which is E8, of course. And you can take all our equations and decompose them with respect to the subgroup. And then you get a theory that has formally E8 invariance, and you can choose now the solution to this section constraint that I keep mentioning, where nothing depends on the 8 internal directions, which is like reduction to, and then you get E8. So our theory gives this as a consequence, but it's not the best way of getting it, to be honest.
Okay, but there is no symmetry of equations of motion at the level more than E8, right? The maximal symmetry of equations of motion for maybe three dimensionals, well, n equals 8 supergravity is E8, but not more. Is it correct?
Yeah, we don't see anything more. Yeah.
Okay. Thank you.
Yeah.
Thank you.
That's right.
Okay. Are there more questions? I have one last curiosity. Can you comment on the, if you want to briefly, the relation with the other approaches? I mean, up to E10, more or less, I can understand how they get there. And then this E11, which pops up naturally in some sense for you and for Peter West. What are the differences and the parallels, the correlations between the two approaches, that the one that you're following, the one that Peter West has been?
So let me, of course, I mean, what I'm going to say now depends on my understanding
of what
Peter West is doing.
Informally, it's an informal
discussion. If I'm misrepresenting him, it's not out of ill will. But so what he is doing, he's also having this infinite set of coordinates as we have, and we took it from him basically. But one important difference is, as far as I can see, the section constraint that I keep mentioning is not anything that he imposes. So he's really trying to do field theory on an infinite dimensional space. And there are some problems associated with that. And we are not facing these problems because we're imposing the section constraint, so which is really important for us. So this is one difference. And another difference is that we are adding things on top of E11. So one of the papers actually that we wrote is called Beyond E11, because we have these extra Stückelberg-like fields. I call them constrained fields in the talk. So we have things which are not within E11, but which are sort of natural in the context of other exceptional field theories that you have to package together with E11, and only then we can make all the symmetries work. So these are sort of two main differences, I would say.
Okay, thank you very much. I would move, thank you very much, Axel, for the talk and for the discussion. And I would go back to Slava, and we have a few more minutes and we can close the session. Slava?
Yes, I'm here.
You're there. Okay, very good. So let's see if we can have another bit of discussion of your interesting work to understand a little bit things for other viewpoints. Let me first let other people ask, and then we will intervene. Now, Carlo Iazzeola has one question. Carlo, please.
Yeah. Hi. Hi, Augusto. Hi, Slava.
Hi.
Hi, everyone. Nice to see you. And no, I had actually one question related to your talk, actually many questions, but let me start first with the following. So do I understand correctly that the solution, the Weil tensors are type D on these solutions, despite the fact that the element K squares to 0? Okay, so these are genuine solutions built out of, at least there are 2 principal spinors in there, not just one. One question I wanted to ask is the following. This for me complicates a little bit the interpretation in the following sense, that for the black holes, there was a clear relation between black hole, say, states, or if you want, local data in the unfolded sense, that were based on that projector, which actually was responsible for the collapse of the nonlinear expansion, if you want, down to first order. And that projector actually was, it was pretty clear what it was, because indeed it's a Fox-based projector, and it's the local data for, in fact, an ADS massless scalar. So this unfolded Penrose transform connects the black hole static state, if you want, to an ADS scalar, massless scalar, like Brighton-Longer-Friedman scalar. Is it clear what is connected in this case to the the black brane solution? What sort of linear solution is actually connected to this via the unfolded Penrose transform?
So you mean, what should I take as a initial data for a Penrose transform to reproduce just gravity sector? Is that the question?
The question is that there's a Fox-based projector here too, right? That you multiply with delta 2 of y to construct.
Yeah, but it's different in a sense that it's related to a single spin. So the difference with this, the case that you're considering, is that there the Fox projector is a bunch of infinite tower spins. Here's this for a single one. So it's just the structure of a high derivative tail of a concrete spin S that form this projector.
But yes, but you remember though that the projector in the case of the black hole was simply, once you strip off the x dependence via gauge function, if you want, it's just simply e to the minus 4e. So it's just literally it's initial local data for a scalar. That's what I mean. In this case, instead, is what? If you already have an answer, I mean.
I have to think. I cannot immediately relate this. A bit different.
Right. Yeah. Yes, I was wondering what was the group theoretic interpretation, in other words, of this.
Okay, I will think.
Yeah. Okay. Thank you.
Are there other questions? So maybe we're running a bit late with respect to the schedule, and we can. I can thank the speakers and all the participants in this session, and we can close it, I would say. Thank you, Slava.
Thank you.
Thank you, everyone. Bye.
Thank you. Bye.